Okay, so welcome to our next session. So today we are going to go over with several problems on thermal stress. So we had actually introduced the formula on thermal stress. So to have a recap, thermal stress is simply the, the stress that is induced by a change in temperature, whether the temperature is cooling down or heating up. So when we have a heating up a temperature, or a temperature increase, would mean a stretch on the material, and a cool down, there will be a contraction of the material. So if you notice, in the construction there are some members that needs to have a clearance between the structural members so that it will have a space for this type of deformation, or the deformation caused by the change in temperature. So every material has distinct or various values for the thermal stress coefficient that is expressed in terms of alpha. So the basic formula, or the general formula, is that delta is equal to alpha L delta T, wherein delta here is delta due to temperature, and alpha is the coefficient of thermal expansion of the material. Length is the origin, L here is the original length, delta T is the change in temperature. So simply this is a final temperature less initial temperature. So for alpha, as we can see, alpha is expressed in micrometer per meter degrees Celsius. So we need to express a consistent unit between the numerator and the denominator here, and by we're going to do that. Okay, so the delta T is expressed in degrees Celsius, and then alpha is expressed, ayun, alpha to micrometer per meter degree Celsius. L is in meters. Okay, so for this problem, we have here a structural element or member. We are required to determine the minimum diameter of this steel rod to be able to be fully stretched in the wall, clearance, a temperature change from negative 25 degrees and warmed up to 25 degrees Celsius. So the steel rod carries a tensile load of 8,000 Newton and is limited to a stress of 120 megapascals. So given the alpha, or the coefficient of thermal expansion, and the modulus of elasticity, let us work on this problem now. So first, we should project what are the corresponding deformation involved here in the problem. So I'm just going to copy this. Okay. So as we can see here, there will be a deformation total on this material, wherein this is to be limited by delta. Okay, so this delta is bounded by a limit of stress of 100 mega Newton per square meter, or that is megapascal. So itong deformation na to hindi pwedeng lumampas sa stress na, okay? So this is a condition wherein hindi siya pwedeng lumampas sa allowable stress of 120 megapascal. So now, ano yung composition nitong delta na to? So number one, it is initially subjected to tensile load of 8,000 Newton. So kapag in-stretch mo yan, of course, it will elongate. It will certainly elongate, no? Due to the force P. Okay, so I'll just denote that by delta due to P. And then aside from this tensile load, there is a significant change in temperature, no? So from negative 25 degrees, magiging 25 degrees. So itong negative parang freezing temperature yan. And then it will warm to 25 degrees or positive 25 degrees Celsius. So there will be a corresponding also deformation due to temperature. So as we can see, this delta will compose of deformation due to the axial load 8,000 and the deformation due to the change in temperature. So this is an allegation in particular since we have here a increase or warming temperature. Okay, so therefore from this illustration we can now write the equation. We have the delta is equal to delta due to the axial load plus delta due to temperature. So for delta, so you know the formula of delta, no? That is PL all over AE. So this is actually the allowed delta, okay? Because the allowable is given. So we're going to denote that as allowable. And then, of course, we know that this is PL over AE due to the tensile load. And the tensile load, as we can see, that is 8,000 Newton. Okay? And then, just write ito na idagdag alpha L delta T. Okay? So in here, we do not need to use this equation because this equation could be expressed in terms of sigma P over A. Okay? So I'll just replace that sigma L all over AE. Okay? This is equal to PL over AE due to the temperature plus alpha L delta T. So next, we are going to substitute now the allowable, and the allowable is 120. So yan, 120 times the original length is unfortunately not given. However, as we can see in the equation, L are just the same, similar on both left and the right portion of the equation, so that it will just be cancelled. Okay, so what is left, we can now erase this portion, is all over area. Okay, this is equal to the load is 8,000. Okay, all over the unknown area also, and then we have here 200,000. Okay, plus alpha. So this is 11.7 micrometer. So we need to determine the prefix for that micro. So if we recall the prefixes, that is nano, micro, milli, centi, deci. So I'll just have to write a line here. Deca, hecto, kilo, mega, giga. Okay, so what you do, 10, 10, 10, 10. So we have -1, -2, -3, -6, and then -9. Uh, then we have here 10, 10, 10, 10, 10. So we have 1, 2, 3, 6, 9. Okay, so ganito lang. So anyway, I'll just select this one. We are in micro. So meaning, if we are converting a prefix, converting it to the meter, so we'll just have to multiply it by times 10 raised to -6. So yun. So I'll just write now the alpha 11.7 times 10 raised to -6. Okay. Our delta T is the final temperature, 25, minus the initial temperature. So we will be having here an addition. So basically, ito magiging 50 yan. Okay. And then eventually we will be having an equation having a single unknown, that is the area. Okay, so the area is found to be 266.67. Okay, so this is millimeter, in terms of millimeter squared. And then finally, in order to solve for the corresponding diameter, of course we'll just equate this to the cross-sectional area, which is a circular one. Okay, the area is 266.67. We have a circular cross-section, pi all over 4 times the diameter is unknown, actually, d squared. Okay, so finally the diameter is found to be 18.43 millimeters. Okay, so this is problem number 1. Okay, so moving on to the second problem. Okay, so for the second problem, we have here a steel railroad. So this is one example of a structural member which leaves a space or clearance, and it is a room for expansion whenever there is a heating temperature or warming temperature. Okay, so here it is. The original length is 12 meters, 4 millimeters is the clearance between, and then we are going to determine the temperature where the steel railroad will just touch the other railroad. So the initial temperature is 20 degrees. Okay, so we'll just have to illustrate it. If this is the zoomed section, this is delta temperature, delta due to temperature, which will be equated to 4 millimeters, because the first unknown is referring to the temperature, so that this will expand and will just fill in the space or the gap. Okay, and this fill in is caused by the temperature change. We're going to set a temperature wherein the delta for temperature would be exactly 4 millimeters. So it's very easy. Just write the thermal or deformation due to thermal stress. Okay, delta T is equal to alpha L delta T, and we just substitute that one. So our alpha here is 11.7 times 10 raised to -6 So the original length is found to be equal to 12,000. So delta T is equal to the final temperature, okay, minus the initial temperature. So we will just place that into our equation. And then as we all know, we substitute this initial to be equal to 20 degrees Celsius. Okay, so finally, the final temperature is equal to 48.49 degrees Celsius. Okay, so that's it for the first unknown. So if we wanted a fill in the gap exactly 4 mm, just set the delta 4 mm and then compute for the final temperature. So at this temperature, that the railings will just touch the other railings, ano? And then for the letter B, the stress that will be induced if there were no initial clearance. E paano kung walang space in between? So paano naman yun? Of course, if there is a push, there is a compressive stress, right? And if there is a stretch, there is a tensile stress. Okay? So dito, if we have again a zoom view of our railings, halimbawa ito tutok yan. Tutok yung isang member, no? There will be no clearance in it. And then if we are going to have a temperature equivalent to 48.49 na na-compute natin a while ago. Okay? So this will be having a stretch here. Okay? Mag-i-stretch yan. Itong stretch na yan, this will induce a push on the other railings. Okay? So may stress yan. Anong klaseng stress? Compressive stress. Okay? So this will start to stress. Okay? So we have already computed that one, right? Na yung in this temperature, mag-stretch out siya ng 4 millimeters. So delta temperature due to temperature is equal to the delta due to the push. Okay? And what is that push? Kasi nga tutok yan. This will have a push on the other railings. So we do not need to expand this because we have already determined that at this temperature we have a 4 mm stretch. We'll just have to equate it with PL over AE. Okay? So we know that this is PL over AE again. Stress nga kinukuha natin, so just express that in terms of stress. So sigma L all over E. Okay? So we just substitute. So we are trying to look into the sigma here. So we'll just substitute 12,000 here and the Young's modulus of elasticity. So it is assumed to be 200 gigapascal, or that is 200,000 megapascals. So from this equation we come up with the stress that is induced by the push that is caused by a stretch, no? Yung stretch dito kanina, it will cause a push in the other on the adjacent member. Okay? So for the sigma, we have 66.67 megapascals. Okay? So this is unknown number 2. Okay? Stress that will be induced if there were no initial clearance. Yeah, pag init niyan, tutok yan, yung tinutukan niya na railings, it will be push out, and it will be compressed. And out of that, there will be a compressive stress equivalent to 66.67 megapascals. Okay, so letter C, the stress that will be induced if the temperature is 60 degrees. So we have another case here. I'll just erase this portion. Again, let us establish our space. Okay. So initially we have a 4 mm clearance here. Okay. So we have already computed na yung temperature just touching these other railings is 4 mm at temperature of 48.49 degrees Celsius. So, ngayon, kapag eksakto yan, kapag lumampas ka dyan, again, it will begin to push the other member. So, kapag lumampas ka, say for example, this is a line for delta temperature at 60 degrees Celsius. Ito naman, delta temperature at 48.49. Okay? Magkakaroon na tayo ng yan. This is delta due to push. Okay? So that is delta due to push. And then this is delta due to temperature at 60 degrees Celsius. So ngayon, kitang-kita naman that the delta temperature is the sum of this 4 millimeters, okay, plus delta due to push. So we'll just have to substitute the given here. This is alpha L delta T at 60 degrees Celsius plus 4, and this is sigma L all over E, or PL over AE. So in-express ko na siya sa in terms of stress, because this is the unknown in the problem. Okay, so as we can see, let us substitute. We have here 11.7 times 10 raised to negative 6 multiplied by the original length times the change in temperature. So we have 60 degrees final temperature minus the initial temperature is 20 degrees. So this is equal to 4 plus sigma, this is 12,000, okay, and then E is 200,000. So a single unknown in an equation can right away get the value of sigma. Okay, so we have a value of 26.93 megapascals. Okay, so again, a temperature exceeding to 48.49, kasi nga yung 48.49 eksakto lang to fill in the space here, which is 4 mm. But a certain temperature to exceed this one will cause a push on the other structural member or the railings. Okay, that is delta P. So out of this, we'll just have to formulate our equation, substitute the formulas, and come up with the stress. Okay, but don't get stressed. Ano? Okay, so for next unknown, the final gap if the temperature is 38 degrees Celsius. Okay, so I'll just have to erase this. So again, we will have the zoomed view on these railings. Okay, so the gap is 4 millimeters. So ngayon, kapag less than sa 48.49, bitin, hindi siya aabot hanggang dun sa dulo, or it will not touch the other railings. Say this is delta due to temperature. So this is the unknown. I'll just denote this by x, and we will form an equation that 4 millimeters is equal to the sum of the deformation due to temperature as well as the gap. Okay, so again we substitute alpha L delta T. This is unknown x. So this is 4. Alpha is again 11.7 times 10 raised to negative 6. L is 12,000. So the change in temperature, the final is 38 minus the initial 20. Okay, plus x. So we'll be having a value for x. X here is equal to 1.47 millimeters. Okay, so this completes our solution for this particular problem.